of all, thank you, Professor Prasad and the Department of Design for inviting me for this talk, and I think it's an honor. Thank you. So let me start right away with designers, and for those who are attending my class, or those who have attended my class, you can shut your ears and eyes right now, because this is going to be an overlap, somewhat overlap. For others, I think it's okay. Let me start with designers. Okay, who is a designer? Now, this is a designer from the 17th century, and his name is John Harrison. He was a craftsman, and he was a craftsman who is also immortalized with a beautiful book written by Dava Sobel called Longitude, because his craft solved a problem that was considered the most difficult and important problem of that century, and that is the problem of, he was a carpenter and a clockmaker, and he designed the first marine chronometer, a clock, the clock that could work on the sea. The problem with regular clocks of that time were that they are all pendulum clocks, and pendulum clocks do not work when you have a non-stable surface, and of course boat is a non-stable surface. And this was such an important problem that the royalty, the Spanish royalty, the Portuguese royalty, the Dutch royalty, so it was an important problem, because when you are on the sea on a boat and you do not know the speed at which you know what the speed at which you are going, but if you do not know exactly the amount of time that has elapsed, then of course you cannot figure out where you are going to be after a while, and therefore it is very important. Anyway, so important that they had a price of something like 10,000 British pounds, and we are talking about 1693. This is a very large amount of money, and Galileo tried to solve the problem by creating a stable surface on an unstable surface, which you could not do. Newton thought it was not possible, and it is absolutely a moment of pride to say that a designer solved it. And as I said, John Harrison not made one but made 5 variants. The first one he made when he was 18, and the last one he made when he was 60 plus, and finally managed to get his prize. So 10,000 British pounds would be of the order of $100 million pounds today. So it was a serious prize. So the person who was supposed to give him the prize was also secretly competing with him, and so the royalty eventually had to shut that person down, the astronomer royal, and then get an independent astronomer to look at his idea and the design. This is a different kind of designer. Okay, this one, those days of course smoking was fashionable, and this designer designed a ship that could go across from Britain to United States without having to refill for coal. So it was a large ship, the first steamship that could do that. And of course the difficulty of having refueling is that you have a longer route to follow, because you have to go to the somewhere in coastline in between that you need not go otherwise, which increases the amount of time. But not only that, it increases the risk. Those days it was risky to go through, lot of pirates, and of course it was more expensive. So he came up with that, and his name is Isambard Kingdom Brunel, and this is what I would call an engineering designer. And he not only built ships that did remarkable things, he designed a bridge that you can see up there, and it is called the Avon Gorge Bridge in Bristol, and again a marvel of 19th century British engineering. He was also a horologist, and amazing design, first time that he could do. Not only did he design the bridge, which is interesting, but also designed the aesthetics of the bridge. So if you look at the columns, those columns are inspired by Egyptian temples, and Egyptian temples have a very high stability while being imposing in its look. And you see a little undercarriage there. Maybe I can just use the pointer. Yeah, if you look at that undercarriage here, he was not only designing for use, he was designing for maintenance. because how do you go underneath the bridge and then fix something if something is wrong. It is a remarkably large bridge and does not look very large, which is also to do with its delicate aesthetic. I stood in front in the middle of here not long ago, and the bridge was swaying, and it is quite a deep gorge. As you can see, the river is right down there. It is not a very pleasant jump if you wanted to do one, but it is perfectly safe, after over 100 years now. Now quickly moving up, this is Saul Bass, as you know, who I would call broadly under the category of form designer. Not only did he design these iconic graphics for Psycho and Graduate and many other movies, but also created this remarkable set of logos that are even now in use in one form or the other. Not only did that, he was also into kinetic typography and various other aspects of form. Moving on, my fourth kind of designer is, I am sure all of you know, Dieter Rams, industrial designer, again immortalized by his work in Braun in consumer electronic products. This is one example. There are many others, and of course he has these 10 principles of good design that are as relevant today as it was when he developed those. The fourth kind of designer is somebody from much closer of the time, and his name is James Dyson, and he likes, and he is still alive, he likes designing X-less Y kind of designs. Okay, this is a bladeless fan, and that is a bagless vacuum cleaner, and there are many other products. I think it is beginning to make its inroads in India as well. You will see it in airports and malls. It has started, but many airports have this the air dryer, hand dryer, which has two hands, and then it's an experience. You don't want to go away from it. That is also a good and maybe not so good aspect of good design, that you get attached to it, and this is one of them. The idea is that where he started, that if you have a bag, then bags will clog, and once it clogs, it has less suction, then it stops cleaning properly and so on, in addition to the fact that you have to keep changing it. And so he said, okay, can we do that, and he used what is called cyclone separation as a process for getting rid of it completely. He also has an award called James Dyson Award that celebrates and encourages and inspires the next generation of design engineers. Moving on, we also have somebody that I am sure all of you know, because he is holding Apple Mac, and that is Steve Jobs. Steve Jobs, I had the experience of using one of those Apple Macs for writing my PhD thesis, and it had a tiny little window, screen of this size, and still everybody was excited and proud to use it. Why? Because it had WYSIWYG. What you see is what you get, and those days you did not get what you saw, and therefore it was a remarkable user experience of the time. Of course, now you are used to all the smartphones, which is very different, but he is the one who started the movement where he said tech can be friendly. He initiated this entire business of giving very different colors to products that are meant to be only serious and office. So from this color palette of black and white and grey, it suddenly became really colorful, and not just that, but this enormous effort that he put in to make the effort to use something disappear, and those are very powerful, important elements of bringing user aspects of design into a product. So why am I talking about these 6 kinds? Because these are some of the major different types of designers that have evolved through the centuries of journey of the concept of the designer. So if you look at that, we all started not just in our society, but in other pre-industrial societies around the world. It started with practitioners of craft, people who took responsibility for all aspects of the product. You think of a village cobbler. Village cobbler knew exactly his clientele, exactly who had one foot slightly smaller than others or slightly crooked than the other and so on, who could pay how much, who had what kind of taste and so on. But not just that, but who knew exactly where the material was available and where he could repair and maintain these products up until the time that it had to be disposed, and then that had to be brought back, and he brought it back and then reused whatever he could. So he was like a entire ecosystem of one, right? And that village cobbler today has expanded into a multinational, let's say Nike, where somebody is doing something here, somebody is doing something there, and it's all connected together. So that's our first kind of designer, the form designer. Then industrial revolution came, the first industrial revolution. Now that we are championing the idea of industry 4.0 and 5.0, that is where human power was replaced by mechanical power, and that led to ability for using machines and so on. And as that happened, the formal and functional aspects started getting separated from each other. Different people had to be trained to take responsibility for different aspects of the product, and a new form of designers started getting championed by Bauhaus and Ulm schools in Europe, for instance, who were both inspired by what is called Crystal Palace exhibition in 1910 in the UK, in London. And a number of different variants of designers started coming, the most important being what I would call basket into form designers and industrial designers, where the focus is on aesthetics, usability, meaning and other human factors of design. And specific category within them is what is called product designer or industrial product designer, who are primarily focusing on 3D products and looking at those aspects in the context of that, with the particular intent of using industrial production, i.e. producing the product in multiple numbers rather than one crafted out or a few crafted out. Now in the functional domains, there was a parallel movement that was taking place. So if you look at the evolution, you see the discipline of engineering were starting in schools of Europe, like École de Pont in 1747, and then we had what is called engineering or function designers, and they were looking at aspects such as performance, reliability, robustness, manufacturability, maintainability and so on. And largely the champions of that were the Germanic speaking schools. So what I mean by that, not just Germany, but Germany, Austria, Denmark and much of Scandinavia and so on. And if some of the earliest work are from Rettenbacher and Rolla. Rolla was a professor at Berlin who pioneered the earliest ideas of principles of machine design in the 1850s. And as this evolved further, there was need for people who understood not just one aspect or the other aspect, but again it started coming back together, that there are people who were needed who understood both functional and formal aspects. So we started seeing people like James Dyson reappear, and this was championed among others by the design school at Delft, and they are still running a program called Industrial Design Engineering program, but also a very highly successful master's program, which is a combined program between Royal College of Art and Imperial College London, that together offers. In fact, Dyson actually graduated from that school in that master's program. And in the 21st century, we also saw, and I did not put many slides on that, but you could similarly find an evolution of how to manage resources, design to manage resources. So you found some of the earliest schools again in the European context started in France and then moved around Europe. In India, IISc started the first management school, and then all the IIMs came and so on and so forth. So you can see that a design of management for resources had a root like that, and eventually they all three seem to have come together in activities such as the ones that are championed by Steve Jobs. People who can take responsibility for not just designing one aspect or the other, but also managing resources to go from society, identify opportunities and so on, develop solutions and come back to society to offer that, and the cycle gets continued. So the idea of innovator entrepreneur also started emerging, and as the startup culture started getting its momentum, it became even more relevant that those have to be taught properly. So, Stanford for instance initiated a program, master's program called impact engineering, where this became a major element of teaching. So, technology, business and social knowledge had to come together in this. So, if we now summarize, so that is what I said, that if we look at the Indian context, craft designer or design in craft and design in forms and design of industrial design, all three were initiated by NID at the bachelor's level. At the master's level, of course, IDC came in. The teaching engineering design as a discipline which is not specific to one kind of engineering or the other started by IIT Madras, and the teaching of industrial design engineering and the innovator entrepreneurship were started at my department, at Department of Design and Manufacturing. So, you can see that we have a presence in all of them, and the main message that I want to get across is that we need not just these kind of designers, but many other possible kinds of designers that we need to evolve. They are all necessary for creating a designer ecosystem that work together for the benefit of the society. And this is where I thought I will just quickly run a few slides about IISc and my department. So, this is an aerial view of IISc, and what you see in the middle here, this is the main building, and the first director, Maurice Travers, was a chemist, spent his 5 years just designing that building. And this is a lake that is not far from here, and we get all our water from that. So, if you close further, you see this fairly classical, neoclassical kind of building, and then the same architect actually also designed the main building of COEP, the College of Engineering, Pune. So, IISc is primarily in the areas of science and engineering. We have a small bachelor's program, is completely upside down. It has about 50 departments, 500 faculty members, 5,000 students. The smallest number is in undergraduate, about 400. Next is masters, about 1,000, and the rest is PhD. And we are one of the 3 strategic universities with Boeing outside the US. So, there are a lot of strategic partnerships that IISc has with other universities and other major organizations. My department, Design and Manufacturing, is highly research intensive. We are very lucky to have very good faculty, as the statistic shows, and we also have very good publications and funding. We have about close to 200 crores in the last 10 years and about 1300 publications peer reviewed. So, yeah, so it's well funded. A few points about that these are all disciplines of the artificial, as he says. There are natural sciences like physics or chemistry or biology, but then if you look at economic sciences, management sciences, computer sciences, the artifacts on which these people are working are really artifacts, means they are constructions of human beings, right. You create a management structure, or you create a computational tool, or you create a economy. These are all human constructions, and therefore, what is the science behind human constructions? So, he gave a bunch of lectures at MIT. He was at Carnegie Mellon. He gave a series of lectures at MIT, and MIT press said, oh, these are good lectures, can we put it together and make a book? And here came a book. It's a tiny book, and you can simply download and read it, because it's MIT press has already given away the rights, saying that everybody should read it. So, you can just download and read it. It's 100 pages, tiny book like that. So, what Simon said was this, that if you are going to design something, the first thing is that you don't like something. If you like everything, then you are not going to design anything, right. So, it started with an undesired situation, and here is an example from our villages, that they have to go a long way to find water, and you might say that is bad because it is unsafe, it is time consuming, it is effort intensive, roads are not particularly good, washing and various other things, water gets polluted. And then you think of something that is more desired, and what he calls these goals, and say, for example, can you bring water home? That is one way, right? Can we make roads safer? That is another way. Can we make washing less effort intensive and so on. And then you plan how to change this undesired situation into a more desired situation, and hope that if it is implemented right and used as intended, that this situation will become that situation, right. This is an example, it is a rural washing machine which is intended for women who typically go and take that water to make their job easier, etc. Not necessarily the best solution, just one exemplar. Now, so what is design? A design is a plan. A design as noun is a plan for change, and designing, to design is a way of constructing what change is needed and constructing a plan with which to make that change possible, right. So, it is the underlying blueprint, as it were, of what we see around us and what we do not see but feel, experience, like an organizational design and so on. So when you are designing, constructing or reconstructing both the goal and the plan, okay, it is not only one or the other. So depending on the kind of designer that you are, you may be designing a technical system like a power plant, an educational system like a Montessori method, an aesthetic system like a logo or a piece of art, a legal system and social system and so on. So design, as Nigel Cross says, and I really find that rather nice, is an interdisciplinary discipline, right. And since a design is a plan for intervention, and I took Simon's definition and stressed a number of points within that. One is that it says when implemented, right. So it is a plan for intervention. For you to see what happens, you have to implement it, that is number one. Number two, it is intended to change. You as a designer want it to change in that manner. There is no guarantee that it will change that way. The third is that what is it going to change? It is going to change an undesirable situation. Who is undesirable? Okay, becomes a very important point. When undesirable becomes a very, very important point. How undesirable and where undesirable. So time, space and people are very important. Same thing can be desirable to undesirable. Plastic was incredibly desirable not very long ago, the wonder material as it is, right, and is not as desirable now. The horses were used for a purpose and they were absolutely essential for human movement. They are not anymore. So these things change. And fourth is that into a less undesirable one, it is meant to change to a less. So let us look at what it means. Okay. Number one, designs are not necessarily for physical artifacts. Okay. There are all kinds of non-physical artifacts that we make, and therefore we as designers need to have a generic view of designs, not one or the other, one and the other. Third is, next is that both these kind of situations are essential for designing. What is undesirable, what is not. Therefore we need to understand the life cycle of the systems that we are trying to improve, right, because you do not know where the undesirable will come from. So its stakeholders, their needs and aspirations. Designing involves identifying these situations and developing them. Hence we have to design both the problem and the solution. So that is another thing. Unless we implement, we do not know whether this design is going to work. Therefore implementation is very important aspect of design. So both designing and implementing, realization, services, business are crucial. So we need to have an idea of the entire process of innovation, not only product or only process. The desired change may not happen, right. We are all designers, we have burnt our fingers long enough or multiple times, we know that first time most designs do not work. Why does it not work? Is it because we got the requirements wrong, or did we get the solution wrong? Why did it not work? So that is where the fact that it may not happen is where there is need for design research that will inform us and support us in practicing and educating in design. That is why research into design is so important. because we need to have knowledge and continue to evolve knowledge, just our knowledge of design and the way it affects and gets affected by other factors, that gives us that power of how we can improve the way we design. So, what are the types of knowledge? So, if you listen to the last couple of slides that I have talked about, I think you can see that a pattern can emerge from that. One is that processes are important, people are important, artifact is important. These came from Nigel Croft. Then Lucian Blessing and so on, they added other things, tools, organizations, economy, ecology increasingly are important. And then we know that when we design, we do various kinds of activities, generating ideas, evaluating ideas, selecting ideas and so on, and we apply a variety of criteria, performance, look, safety, cost and so on, and we apply them for improving something or the other in the life cycle of the product, materials phase, production phase, usage phase, end of life phase and so on. And we do that by tinkering between the outcomes, right. Sometimes we are looking at what are the intents that the design is trying to solve, and sometimes we look at the that is the problem, and sometimes on the solution. And we expand that. In the beginning we may be only worrying about what is it that the design is going to do. Later on we are going to say, okay, how big is it going to be, where is it going to fit, can I make it and so on. So, there are multiple stages of design, and sometimes you are working only on a component, maybe only on a mouse or only on the chip, and sometimes you are working, some designers are working on the entire system, okay, or maybe a system of systems like an airport. And these happens through various stages of design, analysis and synthesis, problem solving, problem finding and so on. So, we can create a design space by putting this together. You can see that innovation can happen at the product level, process level, service level, business level. So, that is here, and they can happen in all kinds of application areas, and they can use knowledge from multiple disciplines, and they can happen at various systemic levels, component level, material level, whole system level, and you can maybe focusing on one or multiple parts of the life cycle. So, these are like different axes of knowledge that we need to have if we are going to equip somebody to design well. And you these are the sort of disciplines of knowledge. If you look at the discipline of knowledge, and we need to have the knowledge of the society, right, how does society function, because we are designing for the society. We need to have knowledge of technology, and I am using the word for a more general meaning. This can be functional technologies, formal technologies like how to, what are the ways in which forms work to create particular emotions and so on, and organizational technologies. And similarly, we focus on function, form. If you look at a car, for example, if you are talking about function, you may be talking about fuel efficiency. If you are talking about function, form, you may be talking about attractiveness or ergonomics. If you are looking at organization, maybe you are talking about commercial viability. So, there are different aspects to that. You may be designing for a single phase like just a materials, or a combination like a product service system. You may have a component focus or a subsystem focus like a gear or a gearbox or the entire car, right. You may be focusing only on the mechanical aspects, or you may be working on multi-disciplinary aspects. You may be focusing only on the product or the entire product, process, service, business. So, again, as you can see, if we combine these aspects and say, okay, what is the designer going to do, we will see different views of the designer, right. Every combination will give us a different kind of designer with a different kinds of expertise, and who will require a different subsets of knowledge to be able to be competent to do that. And design sort of passes through that. So, we can actually summarize it by saying we need to have learning or knowledge of innovation aspects, life cycle aspects, systems aspects, disciplinary aspects and design aspects. And I will not get into the detail, but we have done analysis that where we can now put the craft designer, engineering designer, the 6 types of designers that earlier I talked about on the on this side here, on the rows and look at the knowledge of discipline, systems, life cycle, application domain and innovation process, and say, okay, what are the pieces of knowledge among these that are essential for training a craft designer or an industrial designer or an innovator entrepreneur. And so potentially you could use that then in order to design your curriculum by saying that my curriculum must have elements of those pieces of knowledge either as part of what I teach or part of the projects that they do, so that they can acquire these kinds of knowledge and utilize them in their training. So broadly speaking, we need to have a mindset for thinking, design thinking if you wish, a structured process for innovating, but the technological building blocks with which you can design. And again, let me remind, these are not only functional technologies. If you have to design a user interface, you need to know that building blocks of user interface design. If you are going to design something that looks good, you need to know what are the principles of something to look good. So that is what I mean by technological building blocks, and then tools and methods that makes our life easier, right. GNAI being one that is right now ravaging everything. And this is a more detailed list of pieces of knowledge that you may require in order to bring these disciplinary boundaries together for training particular kinds of designer. I will escape that, it is too detailed for this talk. Now from there I wanted to come back to a major area of learning that is often overlooked in our curriculum, and I will come back to that at the end, but let me just quickly run through a study that we did of 12 outstanding innovators. You know most of their names: Archimedes of Greece, Leonardo, James Watt invented an efficient steam engine, Brunel I talked about earlier, Eiffel, railway engineer, Eiffel Tower. He did not design Eiffel Tower, by the way. It's in his name that Eiffel Tower was given a name, designers are different. Edison, efficient light bulb, Graham Bell, telephone, Tesla, induction motor, diesel engine, Henry Ford, assembly line, and Wright brothers, you know, man powered flight, and Honda. Now first of all, I want you to recognize the wide variety, even though they look similar because lot of technologies are involved in these designers, but I need you to recognize that they are at least between at least 3000 years apart, right, from each other. If you look at Archimedes, it's BC and most of the others are AD, but various points in AD. Second is that they are also spaced apart, right. So if you think about US, so US is sort of, if you cut a tunnel right down here, you will end up in the US, right, in the other side. That's how far US is. So that's sort of pi r, right, pi r is the distance. So it's 6400 kilometer. What is the radius of Earth? Oh, it's 3200 kilometers, right. So pi is 3, so that's roughly 3 times that. Okay, so that's a lot of variety, yet, and this is where the yet comes, they have a lot of similarities, remarkable. One is that they are all incredibly curious. Curiosity is your interest in something that has no apparent use for you. That is what curiosity is. Okay, it is undirected, okay, acquisition of knowledge, that is curiosity, lots of curiosity. Diesel, for example, was not only interested in heat engines, which he should be if he has to invent a new kind of heat engine, diesel engine, and chemistry, of course, because fuel has to do something, I understand that, but what about languages and social theory? Okay, he was deeply interested, not just interested in things that may not matter for him, but also to solve problems. Okay, very hard work, okay, very hard working, persevering, patient, self belief, high standard of what is considered success, very keen on acting, learning throughout life, questioning accepted wisdom, knowledge, not just the regular book knowledge, but also hands-on skills. Brunel was sent for 10 years to study how to make a precise clock under a French horologist by his father. Now remember, this is happening at a time when the French and the English are really arch enemies of each other, right. Napoleon is sitting somewhere, St. Helena or somewhere, enjoying retired life. So even then this is important. Why is it important? Why is it important for a railway engineer to know how to make a clock? James Watt was one of the finest makers of telescopes and microscopes of his time, which is why University of Glasgow picked him up as a precision mechanicist, which is why he was called in action when a steam engine designed by somebody called Newcomen about 50 years ago was not working properly, and he was asked to fix it, repair. And when he went and tried to fix it, he realized that it is not just fixing what is not working. There is a more fundamental problem with the design of the steam engine, and he decided to change that design, which is why its efficiency went up by a factor of 10 times better, which is why it became possible for large companies to buy economically buy these machines and use them as prime movers for running their factories, which is why among others the first industrial revolution happened. Okay. So different kinds of knowledge including skills and intuition and so on, but I have specifically an environment happened to support them. Please focus on perseverance and high standard. It understood that if you have a higher standard of what satisfies you, you will require to be far more hardworking to be able to be successful. So why on earth anybody would spend all his time working incredibly hard by putting a very high standard that is almost impossible to achieve? And that is a question that we pondered on for a long time and looked at multiple aspects, and finally came to this conclusion that they were creating knowledge and creating knowledge for people that will change their lives and so on, and it was an incredibly satisfying and challenging activity. So in other words, they were remunerated by the process itself. It is something that you enjoy doing, and I do not have to tell you, your designers, that design is a very enjoyable and frustrating at the same time kind of activity, right. So design was the motivator. So what I wanted to get to is that there is a great need for us to energize the learning that happens in our universities, where students are not simply doing assignments, okay. They are doing it because they see a purpose in doing to come from, and I believe that a major part of that purpose can come by turning the focus to design and saying they are learning because they want to design, and therefore how do I show the relevance of my teaching to designing something that will make it incredibly motivational for all of us. Right, moving on to the fourth topic of today, third topic, anyway never mind, one of those topics, design research, okay. And this is one of my favorite quotes, one of the quotes that is my favorite, not my favorite quotes, and that is from Werner Heisenberg. Of course, I am incredibly fascinated by his insights. One thing I am not at all fascinated by is his support of Hitler and supporting the Nazi Germany, but beyond that I think he was quite remarkable. And what he said was, here what you observe is not nature itself, but nature exposed to our method of questioning. So when you are as a scientist, and it does not matter what kind of scientist, including scientists of design which you are focusing on some phenomena, it is the way we ask our questions that opens or does not open the answers and the type of answers that it opens. is an incredibly deep insight, and this method of questioning is what you call design research methodology. Well, in this case research methodology, and if you apply that to design, then becomes. So, what he is trying to say is that the way you ask questions, basically the way you research, okay, is incredibly important, and it will decide the kind of answers you are going to get, okay, and that makes sense. So, what is research? The word, I am using the word research and science synonymously, because here we are not talking about the research that you do as part of your design process. You are not talking about user research, we are talking about research into design. We are looking at design and designing as phenomena of interest, just like a physicist looks at the behavior of physical systems as its phenomena of interest, a chemist looks at behavior of a chemical system as phenomena of interest, a biologist looks at a biological system as its phenomena of interest. We look at design systems as our phenomena of interest, right. And what is science? Science is systematic study of the phenomena of interest, so that we can develop knowledge about the phenomena. And this knowledge is not just any knowledge, it has to be purposeful. Either it will improve our understanding of the phenomena, or it will improve the phenomena itself. Sometimes both of them will happen together, right. Sometimes both of them will happen together. If you do not know, if the world does not have any natural piezoelectric material, okay, by the way, those who do not know what piezoelectric material is, if you squeeze those materials, the charges will come to the surface and separate. In other words, it will operate like a little battery, okay, it is like battery, and then if I connect that, I can get a little electric flow going. In other words, I can convert my pressure energy into electrical energy, right. Very, very useful thing. We use that in all kinds of devices, including the airbag that opens up when hopefully not accident happens in a car, right. Now, if there is naturally no piezoelectric material, then I can't discover piezoelectric phenomenon, because it is not out there. So, sometimes you have to invent in order to discover. These things are not so separate from each other. Sometimes invention leads to discovery, discovery leads to invention, and then that leads to other discovery and invention, all kinds of permutation and combination. But the point is that our goals are either to improve understanding or to improve the phenomena itself. Can we understand design better? Can we better design, right, both of them, and not before, of course, it has to be novel, and most importantly it has to be generic. It does not make sense to have a whole understanding created for just one thing and I can't reuse it anywhere else. Hence, we give more value to the pieces of knowledge that can be applied to multiple things, can be applied multiple times across multiple situations and so on. And last but not the least, it has to be valid. It is not just my opinion against yours. There has to be a generic truth about it, that whatever I am saying, there has to be an independent way of seeing whether what I am saying is right or not right. Okay? So, it has to be that. So, purposeful, new, generic and valid. How do you create that? How do you do that science? Okay, and particularly in context of design. Now, if you look at design, we have design and designing as we talked about earlier, and we have all these facets as we call them around them, right. There are people who design, there are people who design for people and so on. So, therefore, people must be an important element in design. Similarly, they typically, whether you use knowingly or unknowingly, you always use a process. Okay. So, there is process, there is some product, right. The way we design a logo is very different from the way you design an aircraft. There are methods and tools and knowledge. When people were designing the pyramids, they had very different kind of knowledge at their disposal to when Frank Gehry, for example, designs his, I don't know, Bilbao buildings and so on, right. And Gaudi in between, for instance, created something like La Sagrada Familia. Okay. So, we operate with certain methods, tools and knowledge, and we have to do with whatever we have. At the time when pyramids are being built, we had no knowledge of soil mechanics. So, we could not figure out what is the kind of pressure that the soil can take, we just have to make one and see whether it dips, and that is exactly what happened. If you go to Giza and from the Giza big pyramids, if you go 5 kilometers into away from the city, there is a place called Saqqara. In Saqqara you have the first prototype of pyramids that worked. It is a frustum. It is about 2 stories, maybe 3 stories high, okay, tiny pyramid compared to pyramid standards. Yeah, but that is the first time they managed to get this pile of rocks in a stable format that they could then emulate in the big pyramids. Okay. So, that is the way you do it. When you do not have the science, you have to just try, see if it works, change, see if it works, trial and error. And organization, you always work within an organization, you always work within an ecological constraint, you always work within a micro and a macro economy. So, they are all going to shape the kind of designing you can do and the kind of designs you can create. You cannot create with titanium if you do not know, or if you do not have the ability to make titanium, right. That is why copper age came. Well, if you look at the ages, right, stone age came before iron age. Why? Copper age, why? Because stone age is simply picking up stone, well, not so simply, because still had to get a tool with which to chip it away. So, you have to invent your flint tools, but once you have got your flint tool, you can cut it and you can take it out, well, a bunch of people, and then you can create structure. But to create copper, you have to go to a certain temperature, you have to be able to concentrate heat to get to that temperature, which by the way is much less than what you require for smelting iron, which is why iron came afterwards, right. So, you are always constrained by the amount of knowledge you have, and yet you design. So, when you are looking at these facets of design, designing is about doing all of that within these knowledge of people, product, process, tools, organization, economy and ecology. So, when you are doing research into design, you are also looking at those, the people disciplines like anthropology, ergonomics, psychology, aesthetics and so on, or for the product the natural engineering sciences, or for methods and tools knowledge engineering, software engineering, for process systems engineering, economics, ecological sciences, management sciences and so on. So, you borrow but also adapt so that it can apply to design, and add to that our knowledge of how design happens and so on, and comes design research. It involves knowledge to inform and support practice and education of design, knowledge about design phenomena which are associated with design, which is the knowledge of design in the middle, the green, and the arrows, the relationships with the facets of design. That is what design phenomena is, and because by the very nature it has to be multidisciplinary, because there are some aspects that are coming from human sciences, some from technical sciences and so on and so forth, right. It is a combination typically. So, design research has 2 kinds of outcomes. One is theories that provide understanding, and support that provide ability with which designers can be made better in doing what they do. So, these are some of the examples of kind of things that forms of knowledge that we produce in design research, theories and models of how design happens, but also all these different kinds of tools, right, guidelines, methods, standards, materials, processes, technologies, and of course policy building blocks and so on. So, any human construction that a designer can use as a building block or to empower itself for designing certain things are forms of knowledge that are part of design research. Design research methodology is one step behind design research. So, if design research methodology is a set of research methods and links among them that provide a framework for carrying out design research in a systematic manner. Just like we can do design in a more systematic or a less systematic manner, we can also do design research in a more or less systematic manner. Research methodology, in this case design, but for the entire philosophy of science is filled with methodology for doing science, right. And so, how are they related to each other? So, you think of design, okay, somebody has to design. So, designers are designing stuff, and we are as design researchers producing knowledge with which we want to better inform and better improve those designs, okay, help them do that. And design research methodology is intended to help improve the construction of knowledge through design research, with which we can empower the designer with knowledge. So, it is a longer stick, but hopefully a more powerful one, because you are improving in a deeper sense. So, goal of design research is to support designing by developing knowledge in various forms to improve the chances of producing something designed to be more successful. And success solution can mean all kinds of things, similarly success can mean all kinds of things. Each of our research may have different meaning to success. Somebody may be working on empowering the bottom of the pyramid, and their success is very different from somebody who is trying to empower, let us say, a corporate in improving its profit. I am not trying to make a value judgment which one is better. I am just saying that there are, all of them can come under the realm of design research. So, you need to decide when you are researching what are your goals or the successes that you are after. Your research is supposed to improve. And then these are 4 questions that one can put. What is a successful solution? Because if you are going to improve the chances of producing successful solution, we need to understand success. So, what is successful and what are the criteria for success, and how is successful solution created or not created, okay, in a negative sense. What are the influences on success? How do you improve the chances of being successful? What kind of tools should we develop, and how would you validate, how would you figure out whether these tools are actually going to work or not work, or to what extent. And so, you can say what is meant by success. It can be all kinds of things. A small list is given there. It can be very different from that list. It is just an exemplar. What influences? It can be any facet, any aspect of those facets, people facet, maybe the creativity of people, maybe the economy of the people, and so on. And how can it be better supported? How do you prescribe guidelines, methods, tools to improve designing, and how do you evaluate support to see if it is really going to work for producing that kind of success, right. So, that is the 4 questions. And with Lucian Blessing and Professor Ken Wallace and I, we developed a methodology called DRM. Then Blessing and I spent another 15 years expanding that and detailing that. That is essentially stitches together these 4 questions. Okay, how do I clarify research to identify the criteria for success? How do I carry out descriptive study in order to figure out what is influencing success and how well or badly does it influence right now? And then we carry out prescriptive study to figure out how to improve that situation with new prescriptions, and we carry out another descriptive study, we call it second descriptive study, in order to see whether that prescription works and to what extent. And of course, more often than not, it is not going to work fully, just like any other design. And so, you need to go back, and we can go back a little bit, which is the smaller arrow, or a little more, which is the bigger arrow, and so on, in order to go cycle through that until it is satisfactory. So, that is basically what DRM is, and you can see that broadly speaking, the first 2 stages are theory development and evaluation. So, developing understanding and evaluating that, and the next 2 are developing support and evaluating that. So, we can put a little bird cage by saying theory, support, and understanding and evaluation, and that is the 4 sort of phases of research. Finally, and this is a question that many times people ask, so I am just put a slide there. What kind of research am I going to do? It's an often asked question. So, you know, I think you know this, I am just repeating probably, but what are the research questions and hypotheses that you are trying to answer or test, right? Eventually, it has to boil down to that. And what is a research question? Research question is a question for which there is no definitive answer. Research hypothesis is a question for which there is an yes or no answer, and then we test that, and it needs to be, the research questions, the hypotheses need to be academically worthwhile, they have to be novel, we said that, purposeful, valid and generic. So, how generic is it? How are you going to validate it? What purpose is it going to serve, and how novel is it? Those are the questions that we ask, primarily by carrying out literature review. Then we asked also the question, because this is design, and design is very strongly linked to practice, unlike many other disciplines. So, we ask also the question of, is it practically worthwhile or industrially worthwhile? So, what is its potential? If you produce your research outcomes, who is it going to help? Okay. Not immediately, it may not be immediately, but at some point of time, right. So, what is the longer term goal? Is it going to inform? Is it going to improve? Is it going to improve practice? It is going to improve education? What is it going to improve? So, what is the potential and what is the eventual impact for practice or education? And then the question is, how will these be answered, these research questions, hypotheses be answered using your research methodology? Okay. And will this methodology produce generic results? Will this methodology produce results that are valid? That is basically what we do in research in a nutshell or in a slide. And with that I will stop. That is the face of the book, and that is the thank you. Thank you. So, if you are going to research, no matter where you are going to research, just to give you the broad, first of all give you some assurance that at least 25-30 disciplines have used DRM. That includes sustainability research. It heavily uses DRM especially in Scandinavian countries. Let me take an example. Okay, let us say that, and this is something, because I can give that example because we did research on that. Let us say that we want to ask the question, how can you use how can you use life cycle assessment, which is a heavily used way of assessing life cycle impact of a product or a solution, a system, early in design process. Because if we can use early in design process, then we have greater chances of improving our product. Right now LCA is used later in design, by that time most decisions are taken, so therefore we cannot really easily change it, right. But the problem of doing that is that you do not know a great deal about the design at that time, whereas LCA requires a lot of data. Data does not exist at that time. So, but okay, let me give you a general answer to your question first. Whatever your research is, that what are the questions you are trying to answer as part of your research, and then you have to answer the question, how are you going to answer those questions? The research methodology comes in answering the second question, but it also comes in figuring out those first questions, but for that you have to read a little more. But that is my general answer. My specific answer to sustainability research is that we did that study, for example, using DRM, and what we did was we identified that you ought to be able to apply LCA. If you have to apply LCA early on, then you ought to accept the fact that you will have lack of data or you will not have precise data. You may know that a product will use steel, but you may not know what steel. You may know that it is going to use metal, but not which metal, or polymer, but not which polymer. Now, how do you take a decision LCA when you know it is a polymer, but not which polymer? So, what you are going to get eventually, so you can boil that down to a series of questions, and then you can apply that to say, okay, right, how do we do that? And what we came up with eventually is a framework where you not only find an answer saying the life cycle assessment result is X in some eco point or something, but our confidence is that answer is Y in some percentage. Now, when you have this together, then it becomes very interesting. Let us say you know nothing about something, what impact it will have on environment. When you do an LCA, you get a value of 0, so, right, because you know nothing, right. Therefore, there is no life cycle impact that you can calculate. So, it will appear to be a very nice product because it has 0 impact, but it is because of your ignorance and not because of actual goodness of the product. So, how do you capture that? So, we bring in this confidence value, saying that I know nothing, but that is because right now we are ignorant, our confidence is 0, compared to another one where its impact is actually 0. So, then our confidence will be 100%. So, while the LCA value is exactly the same, confidence value is dramatically different. So, how do you bring this confidence value and LCA value together into a decision making framework to say what to do when you have a certain combination of those? And if you apply that, sometimes you do not take a decision but defer decision and collect more data or wait for more development, which is a better thing to do than arbitrarily decide. So, that is one way, for example, one example of application.